Oh, wait a minute. Now that we're starting class, let's begin again. I'll start. Dear Heavenly Father, we thank you for this day. We thank you for your grace and forgiveness. I pray that the students would remember they should behave like you. In the name we pray that Jesus, amen. Okay, so what he points out is that minus the absolute value of a sub k is less than or equal to a sub k is less than or equal to the absolute value of a sub k. So me being clever, quote unquote, in the time before class, no, this is what we can say. This is true whether a sub k is positive or negative, right? If you have this, then it's trivial almost to get to what we had before. Add the absolute value of a sub k across this inequality, right? What does that give us? So now it's immediate. I think in order to have seen this inequality in the way we were doing it before class time, man, you guys got here just on time today. It's good. So it would have actually required case-wise logic to see our way to this, I think. And that's why we wouldn't have found it for a while. Sorry about that. Okay, so now that you have this, if the sum, right, of a sub k, converges, what does that mean? That implies that the nth partial sum, if we look at the sum, k equals 0 to n of the absolute value of a sub k, right, that converges, right? Goes to L for some L, right? And now we can do basic, so we can do basic comparison tests, right? So like, likewise, I guess I still don't need to talk about the partial sums here perhaps, but this converges, right? So look at it. Then if you look at the partial sum, right? K equals 0 to n of, I'm getting distracted here. I don't need to look at partial sums. What test should I use to finish this argument? Basic comparison, right? So notice that the sum, okay, k equals 0 to infinity of 2 times the absolute value sub k converges. Therefore, the sum of a sub k plus the absolute value of a sub k, maybe I do need to think about I don't know. I mean, there's a theorem we're missing here, converges, right? What am I after? So like the theorem we need here at the moment is the following, right? If the sum over a converges, a sub k converges. I shouldn't use a. Let me use something else, something neutral. If the sum over alpha sub k converges, and the sum over alpha sub k plus beta sub k converges, then what? The sum of beta sub k converges. All right. That's the pattern we have here right now, right? So like, what do I have? I have that the sum over the absolute value of a sub k converges. And I have what? The sum over a sub k plus the uh, um, the absolute value of a sub k plus a sub k converges. So it follows then that what? The sum of a sub k converges. Now, how do I know that? I mean, we never proved that theorem. The way to prove that theorem is just to look at partial sums and think about limits, right? So what I was doing in the green, if you want to understand the theorem I just wrote here, which you might call a lemma, if you want to understand the lemma, you probably have to look at the partial sums I'm talking about in green. All right, I'm going to stop talking about this. The takeaway message here is very simple. Absolute convergence implies convergence, all right? So that's sometimes very nice, right? Because if you've got something that's like something that behaves very nicely under the integral test, right? Like a typical place where you'd use this theorem is the following example. If I had something like, you know, the sum over n e to the minus n squared or something like that, I think this would be an example. And, oh, I'm sorry, I'm using n equals 1 to infinity, right? And I take this lovely, this is not a bad example. You could show this converges by the integral test, right? Do you agree? You'd make a u substitution, u equals, you know, minus x squared. Think about f of x is equal to x e to the minus x squared. The antiderivative is what? E to the, basically some some constant, like what, minus a half times e to the minus x squared. And that behaves well as x goes to infinity. This converges because the corresponding integral converges, right? Great. What if you have minus 1 to the n on the formula? Oh, man. See, now it's a mess. Sometimes it's positive, sometimes it's negative. I can't do the integral test of that, right? But I can easily take the absolute value of that series, right? And then I can show that converges by this theorem I almost proved today. Sorry. The proof is in page 597. Whatever I have muddled, he has there, and it's 3 lines. So you can easily prove the absolute value of this series converges by the integral test. Then by this theorem, it follows that that converges. That's actually a way that this theorem is used. Okay. All right, let me get back to the alternating series test. So what was that test? If we have B0, B1, B2, positive and decreasing, right? Then, maybe not if then, this is given this, right? The sum k equals 0 to infinity of minus 1 to the k, b sub k converges if and only if what? What would I do?
That's the alternating series test?
No, this right here, what I'm doing? Yeah. This is merely the proof, the statement that absolutely convergent series are also convergent series. It's the very first thing that's proved. It's theorem 12.5.1 and 597. Sorry about that. So it's not even. I didn't even mention it yesterday. I got lost in my false exuberance that I was going to give a correct proof of the alternating series test. I'm going to try to do that today. So b sub k goes to 0. I mean, these are quite different theorems, right? to be completely honest, this one is way more useful than that one, actually. Okay, so here's what I got confused about yesterday. As I talked about the partial sums yesterday, okay, so the one proof we did was fine. This direction, if this converges, that must go to 0. This direction of the proof. The proof yesterday, it's not hard, okay? What we did yesterday is cool. Just to reiterate, if that series converges, that means that minus 1 to the k times b sub k goes to 0. But if minus 1 times b to the k goes to 0, then the absolute value of minus 1 times b to the k goes to 0, which is just b to the k. B sub k goes to 0. So this direction is just kth term test, and the fact that if a sequence goes to 0, the absolute value of the sequence also goes to 0. The other direction, though, what I said was total nonsense yesterday. Unadulterated, total nonsense. You guys should have stopped me. Yeah, should have stopped me. And so my conceptual error yesterday in reading his proof and trying to explain it to you guys was I was thinking when he talked about the even partial sums or the odd partial sums, I thought he was still talking about partial sums for the series we're considering. But actually what he's doing is more interesting than that. So if we look at like the nth partial sum here, so we're going to assume b sub k goes to 0, okay? And then consider the following. If we look at the nth partial sum, all right, which would be what? This would be like b naught minus b1 plus b2 minus b3 plus dot, 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 dot. I'm not sure, plus or minus, b sub n. What he does, okay, is he rewrites this, right? He thinks about this instead as being like, I don't even know what the right notation is for it, but this would be like b naught plus b2, right? Plus b4 plus da 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 da. I guess I need to be specific here. Let's suppose that n is, what do you want to make n, even or odd? We just got to get started, either even or odd. What do you want? Even, okay. If it's even, then this is a plus, right? And so you could rewrite this as b0 plus b2 plus b4 plus da 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 plus bn. And then what? Minus what? b1 plus b3 plus da 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 plus bn minus 1, right? So what he does is he splits we basically look at, and he separately analyzes the sum of the even terms and the sum of the odd terms. He really looks at what are called subsequences of the sequence of partial sums, the even subsequence and the odd subsequence. So yeah. That is not what he does either. I have been talked into something that's still not. I tell you what, I'm sorry. I'm gonna stop here. I don't trust myself anything. I admit defeat. Sometimes you have to know when a battle is lost, and it's lost at the moment. I'm gonna stop right here, and let you have the rest of the time for homework. So I will hopefully fix this in the later section, and then I'll point you to a ref. I'm sorry. I'm not at all happy about this. I know you guys care infinitely less about proofs than I do, but it's very bothersome to me when I don't prove something properly in here. All right, you got questions about homework, let me take them. And there, folks, is the difference between Calculus 1 and Calculus 2. It never happens to, this doesn't happen to me in Calculus 1. I tell you, Calculus 2, parts of it are just difficult, you know? Who here hasn't gotten their homework 6 back? I think these are I'm mostly looking here, I think, at section 2 folks. So, because I think I gave it back to you guys. I think, yeah. Only found one. That's yours. There you go. Sorry. Sorry, I'm very annoyed by this. Let me stop talking about it. Okay, so one of the things I was supposed to talk about was problem 44. All right, let me start with that. Problem 44 is about estimation. And this, I'm talking about section, what was it, 12.3, I think? So if you look at problem 40, there's this magical formula, right? And there's a larger comment to make here. And I did this before, but let me talk to you about it again. So if we have a continuous decreasing positive function from 1 to infinity, right? Like this. Remember, we can look at, what can we do? We can look on the one hand at like this, right? And so forth. But on the other hand, we also have, so this would be what? This would be like f of 2, f of 3, f of 4, and so forth. But if on the other hand, you look at, based on the left endpoint rule, these red boxes, right? Red box. This would be like f of 1, f of 2, f of 3, right? So we have the following. We have that the sum, let's see here, the sum k equals 2 to infinity of f of k is less than or equal to the integral from 1 to infinity of f of x dx, right? Is less than or equal to the sum of what? K equals 1 to infinity of f of k, assuming it's converging, of course. So this, I suppose, gives you a kind of, so what could we use that for some kind of estimate here? See, number 40 in section 4.3, he has the difference between what? Let's see here. Oh, I'm sorry. I'm getting. If we look at that more carefully, what does he have? It's 1 over. Oh man, nothing's going the right way for me today. I guess instead of looking at infinity, I should look at n, right? Suppose this just goes out here to n, right? Then what would this look like? Where does this stop and where does the other one stop? It's a little bit of a difference, right? It goes from 2, right, all the way to what? To n, right? It goes from 1 all the way to what? n minus 1, yeah. So what does that tell me? Of course, this is also equal to what, if you'll allow me this small manga-style calculation. This is f of n plus, oh man, well, fine. Ah, curses. I'm running out of room here. So of course that's f of n plus, what if I want to make that sum k equals 1 to n of f of k? What have I done if I do that? See, this is at 2. That starts at, if I make that 1, to be fair, I have to do what? I have to subtract f of 1, yeah. But then over here, this is what? Sum k equals 1 to n of f of k, right? Minus f of n. And I think I can play with this to come up with an estimate for the nth partial sum as it relates to the integral. Right? But I don't know, maybe I should just go home, I don't know. Look, if you look at problem 40, you can use that to do problem 44, okay? That's the point there. You don't have to prove problem 40. You can use number 40 to do problem 44 in your homework, okay? But I really do think that problem 40 is derived from this kind of argument. And then you let like n go to infinity. If I understand things correctly here. Well, it's a combination of the integral test and this or something like that. I'm going to shut up about it. Do you guys have questions about your homework? Please put me out of my misery. 25 and 12.1. All right. Let's see here. Ah. Interesting. Number 25 in section 12.1. Here we have 0.A1, A2, A3, A4, right? So, what is that? It's not like a classroom leaving, because it's like someone is just taking one chair and just going like, it's very strange. What's going on? Oh, just to n, huh? It's kind of conspiracy, I see here. So of course, I mean, you can rewrite this as what? 0.A1 plus 0.0A2 plus plus 0.00, however many zeros you need, AN, right? Am I wrong? And then this is really what? This is really like A1 over 10, right? Plus A2 over 100, right? Plus plus AN divided by what? Yeah, 10 to the n. So in nicer notation with this would be what? Sum. Let's say n equals, or k, yeah. N equals 1 to, oh, n is a bad. No. No can do. K. N is already used up here, right? N is not free. Well, n is free. I can't make it a dummy. Okay, k equals 1 to n, yeah. What do you say? A sub k, a sub k divided by what? 10 to the k, yeah. So there you go. That's the decimal expansion there written in summation notation, or sigma notation as it's called. of course, as n goes to infinity, you get a series, right? Other questions? Thank you. I feel like I could do something again after a dark time. Yes?
Number 10 and
12.2, number 10. Yeah, just cancel class in the next session. Just call it a day. Let's see, was it number 10? This one's not too bad. This one, so 3 to the k minus 1 over 4 to the 3k plus 1. So k is equal to 0 to infinity. We're supposed to find the sum? Are we supposed to just calculate the series, the sum of the series? I think we are. Find if it's convergent. If it is convergent, find its sum is the instructions. Chewbacca. Let's see here. So, look, your target is this. We know that if we have a r to the k equals 0 to infinity, right? That's equal to a over 1 minus r, provided what? The absolute value of r is less than 1. So, you see, I need to somehow rewrite this so that it's a constant times something to the k power. That's one way to think about this, right? What's another way to think about this? If I want to find the ratio, I can take the ratio of subsequent elements, right? If I look at, by the way, this has what? R equal to a sub k plus 1 divided by a sub k, right? Constant. What was the question? No? So, I mean, there's two different ways I can do this. The one is to be sneaky and just to rewrite it. If I'm sneaky and I rewrite it, I would look at this, I go, aha. I can just go, okay, so that's k equals 0 to infinity of like 3 to the k over 4 to the 3k. And then I've got stuff. I've got like a 1/12 out here, right? And then that's the sum, k equals 0 to infinity. Let's see here. That's what? That's 1/12. 3 over 64 to the k power, because 4 cubed is 64. So it's geometric with the initial term being 1/12 and the ratio being 3/64. Right? Well, there's a k minus 1 here, so that's a third. There's a plus 1 here, that's a 4. So minus 3 to the minus 1 over 4 downstairs is 1 over 3 times 4, which is 12. It's also the thing we get from putting k equal to 0. Now, I know, so that's one way of thinking about this, right? And then once you have that, of course, it's, 1/12 over 1 minus 3 over 64 by the geometric series result, right? Which you should simplify. You can simplify that, right? But just to show you, if we did take 3 to the k plus 1 minus 1 divided by 4 to the 3 times parentheses k plus 1 plus 1, and if we divided that, right, by 3 to the k minus 1 over 4 times 3 to the k plus 1, we could have derived that 3/64. We could have seen that that's what we should find if we take the ratio of subsequent elements also. It's the same algebra, basically. This is 3 to the k times 4 to the 3k plus 1 divided by 4 to the 3k plus 4 times 3 to the k minus 1, which is equal to 3 to the k minus 1 times 4 to the 3k plus 1, parentheses, minus 3k plus 4. See what that is, though. The k's cancel, and you're just left with 3 times 4 to the minus 3, also known as 3/64. So if you have an intuition that something's geometric, but you can't quite see how to... Uh-oh. My audio has probably been scratchy for a while. You can't quite see how to, do the algebra I did. Sometimes it might be helpful to look at the ratio of subsequent elements and find out, is it really geometric, right? Because if it's not really geometric and you try to do this calculation, you won't get something independent of k. But if it really is geometric, then they'll work out to just a number. If that number is less than 1 in magnitude, it's convergent, right? Because that's a convergent geometric series. I'm going to shut up. Other questions? 12.216? Okay. Find a series expansion for the expression x over 1 plus x. Okay, so here's what I'm going to do for this one. I'm going to rewrite this, plus x, right? Plus x?
X over 1 plus x, the absolute value of x is less than 1.
Oh, that's good. All right. Check this out. So this is equal to what? This is equal to x over 1 minus a minus x, right? So all these problems are, right, it's just pattern matching. All we have to do is basically just pattern matching to the geometric series result. So you look at what we have. The reason I wrote it as a minus is so I could make the pattern clear, right? So you look at this, right? And you compare it to this. So what's a equals to? R negative x, yeah. So this is, in fact, if we want to rewrite this as a series, it's just straight up the sum, k equals 0 to infinity, of x times minus x to the k-fold power. And I can clean that up a little bit. Let me do that. K equals 0 to infinity of minus 1 to the k times x to the k plus 1. And for what it's worth, it's kind of fun to just write out what that looks like. That's like x minus x squared plus x cubed minus x to the 4th plus dot 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 dot. Now, we've done all of this assuming what? X is a fixed number, right? With absolute value less than 1. So, of course, minus x also has absolute value less than 1. So the geometric series applies. By the way, this is really cool. This is an example of a power series expansion. This function, f of x, this rational function, x over 1 plus x, right, can be rewritten as this unending polynomial over here. This is called a power series. Because we can do this not just for 1x, but for like each x. So this is actually, but anyway, more on that later once I get past my... We're going on to power series tomorrow. I'm not going to waste another of your days to watch me not prove alternating series test stuff. So we will go on. Not this, but sorry. I'll get over it. Yes. You have homework on it. The homework is clear whether or not my proof is clear. I will work.
Do you just need to know like the theorem, or like will we need to be?
You need to be able to apply the theorem to problems. So, no, you won't. I don't think you'll have to prove it. I mean, it's maybe some other semester, but certainly not this one. I mean, if I have not given you a clear proof in class, I don't think it's fair to ask that of you. No. In fact, I don't think it's going to be the case that I ask you to prove the theorems from this chapter 12. What I'll ask you to do is to apply them. That is plenty of, that is hard enough. more than enough to learn there without forcing you to also learn the proofs of the theorems. I show you the proofs of the theorems so that you understand what the test is built over and why it's working, because that in part will give you some intuition for whether or not it's going to work on a given problem if you think about things. Okay, so next question. What's that? 14, 12.3. Well, it's yeah, we did that yesterday, but I understand. And so let's just tell her, what did we do? We did basic comparison to 1 over 2k. That's not at all obvious, though. It took us a little work to come up with the comparison. So you can show 1 over 1 plus 2 ln k is greater than or equal to 1 over 2k. Then use the basic comparison test. I'll post the video later today. In the video, I show how you can show that using calculus. It's somewhat involved. Well, sorry guys, I know we're out of time, so I'll take another question if you want to ask me, but you know, nothing sticks out. How about this? If you want to ask me the question, I'll answer it in the next section. 32 from 12.3. Yeah. That one is less than or equal to 1. No, that's greater than or equal to 1 over the square root of k plus 1. Because cosine goes between -1 and 1, so the smallest the numerator can possibly be is 1. So that's greater than or equal to 1 over the square root of k plus 1. And you can show that 1 over the square root of k plus 1 diverges, either through integral test or just playing with the p equals a half case a little bit and shifting it, or by limit comparison also. Yeah.